review with a lab here. This is stuff that we hit last time in class, but I want to go back over it because it's important. It brings together a lot of the things that we've already learned. If you haven't noticed, chemistry is a building thing, just like math. So if you don't know the stuff before, it makes it harder as you go. So please make sure you're coming in and getting some help with the things that you need. All right, so this is how I do it when I have to figure out what equation is going to make. First thing I do is go sodium. Okay, I know that's an Na, and I know it's a positive. Carbonate is on the back side of your periodic table, and it's CO3, and it's a 2 minus. So then I stop because it says plus. I know those two have to go together and add to equal 0. So I'm going to need 2 sodiums to go with 1 carbonate, and then I can go forward. Everything that we're doing in this lab is going to be aqueous on the reactant side. On the product side, you're going to have to figure out what it is. Okay, so on this next one, silver is part of the slide. It's Ag with a +1. Nitrate we've used a lot, NO3, it's a -1. +1, -1, I just smash them together. Now, if you remember, in chemistry, we don't do foil, we do OI. So outsides and insides are going to go together. So sodium is going to go with nitrate on the other side. It's +1, -1, so NaNO3. And if I stop right there, I can say, okay, NAGSAG, is it going to be soluble? So N is nitrates. Right there, I've got something that I have because it's silver nitrate. Because it's part of NAGSAG, it is AQ. And I can go on to the next thing. Sodium is also in there as group 17 metals, so we can use either one of those. The next ones we want to do are silver with carbonate. So we did the outsides, now we're doing the insides. Always write your positives first. So the silver is a +1 and carbonate is a -2. So we're going to need 2 silvers to go with 1 carbonate. Now I'm going to go through the NAGSAG. Is there a nitrate there? No. Is there an acetate there? No. Is there a group 1 metal there? No. Is there sulfate there? No. Is there an ammonia there? No. And is there a group 17 metal there? No. All of them are no, so this becomes a solid. Okay? I sort of split my 2 up because I didn't have enough room on this one, so I'm going to put my 2 here. My 2 is what was my solid? Well, we just figured that out. It was Ag2CO3. I do need to balance it. Let's see, did you get a, need a polar, what was it calling? Yeah, I don't know where I put them. Sorry, little interruption here. And no, and no, and no. Seek and you shall find. Okay, so we do need to balance this top one. I didn't balance it really quickly. There's just 2 numbers I need to put in. Anybody see what they are real quick? You can go ahead and bump a scratch paper up and balance side to side. But if you look really quick, sodium, there's 2 on this side. There's only 1 on that side. So I'm going to put a 2 right here. And then that makes 2 sodiums. It also makes 2 nitrates. Since nitrates hang together, I can sort of take them as being a group on both sides. So I need 2 on this side, 2 silvers, 1 carbonate, 1 carbonate. So I'm balanced. Now, number 3 asks, what are the spectator ions? Do you remember what they were? Those are what doesn't make up the solid. So what ions on the product side didn't make up the solid? Sodium, so we would write Na plus, and that would be AQ. And what else? Nitrate, so NO3 minus, and it would be AQ. Okay, the last one here is we have to write the net ionic equation. Remember I told you a little trick to do that? We could break that whole thing up, and they'll have you do that all into ions. So anything that's AQ breaks up into its ions. By the way, that was AQ too. But anything that's solid stays together. Well, we cancel out our spectator ions on both sides. So basically our net ionic equation just ends up being pointing to our solid And okay, what ions made up that solid? Well, I needed how many silvers? 2 Ag plus Aq. And I needed 1 CO3, 2 minus Aq. That's my net ionic. So I just write what ions make up my solid. Okay? Okay, we're going to do a few of these together, and then I'll give you some time to do more on your own, because I want you to have a chance to do these on your own. Okay, so the next one I'm going to do is G. I think that's, yeah, G's next. So find G. I'm not going to go in. Oh, by the way, on this one, once we found out the solid, if you'll go to the second to last page, the last page, by the way, is a blank page, so if you want to pull it off and use it as your scratch paper to balance your equations, it wasn't meant to actually print the last page, but that gives you a scratch paper so you can balance your equations. On the very back page right here, there is 2 grids. The big grid is for when we're in lab. The little grid is where you're going to put your predictions. So we just predicted on this first one, on A, that we would get Ag2CO3 as a solid. So you're going to find in that grid where AgNO3 and NaCO3 cross. Okay, see where they cross right there? First column, first row. You're going to put Ag2CO3. So if we get a solid, that's what the solid's going to be there. Okay, so when we mix it. So go ahead and put right in that thing right there, Ag2CO3. All right, so now you found G. Go ahead and take all this down too. On G, again, I break it down, just like when we were just starting to learn how to put together formulas, right? So sodium is Na with a plus, and I do write it right above it, okay, because then I'm going to use my OI to figure out the others. Phosphate, PO4 with a 3 minus. Lead 2, remember the Roman numeral tells me the charge on the lead, so it's Pb 2 plus. And nitrate we just had as NO3 minus. Okay, so the first one before the plus, because the plus tells me there's 2 different compounds, is the Na and the PO4. PO4 has a minus 3 charge, Na only has a plus 1, so I'm going to need 3 plus 1s to balance out the negative 3. So Na3, PO4. In NAGSAG, this is group 1 metals. So this is aqueous, but I already told you everything on the reactant side is going to be AQ. Then we're going to go plus. We got Pb plus 2 and NO3 with a minus 1. So this time I'm going to need 2 of the minus 1s to add to the plus 2 to add to 0. So we're going to go Pb parentheses NO3 parentheses 2. And this is a nitrate. That's the N on NAGSAG, and it is aqueous. Now we're going to do OI, outsides and insides. So sodium is going with nitrate. We've done this one before, NaNO3. This is group 1 metal and nitrates, both, so this is aqueous. Plus, insides go together. Remember, we always write a positive first, so lead and phosphate. Now here we've got a plus 2 and a minus 3. So we've got to go with a common factor, which is 6. So how many leads do I need? 3, good. How many phosphates do I need? 2. And I need to make sure I put that phosphate in a group. Okay, let's go through NAGSAG. Is there nitrates? No. Is there acetates? No. Is there group 1 metal? No. Is there sulfates? No. Is there ammonia? No. And is there group 17 metals or nonmetals? No. So this one is going to be my solid. And there might be some that don't have any solids, so make sure you're going through that NAGSAG. Remember that sulfates have an exception with PMS and castor bear, and group 17 metals have exception with PMS. Okay? All right, so here we put here PB3PO4. Ooh, I forgot to do one thing. Can anybody tell me what I forgot? To balance it. This one gets a little hairy. I'll give you a little hint. This is a 6. What do the other things need to be? So what am I going to put here in front of the Na? 2. What am I going to put in front of the PB? 3. Okay, and then everything else should be balanced. Okay, so the thing that clued me off real quickly is if I was looking here, PB, it's a 3, and nitrates had to be a 2. So if I put a 3 in front of here, then I'd need to have 6 nitrates. That was the thing that cued me off. So you could have gone through and said, oh, 3 and 3, and then you have to go back and fix it. Okay, so what are my spectator ions? Which ones are not used to make up my solid here? Yeah. It's up to you. If there's room, great. If there's not, take them down. Or if you get tired of them, take them down. Okay. What are they? They're the same ones, right? What makes up Na plus AQ? And that's a funny Q, sorry. And NO3 minus AQ. Right? All right, so the last one I'm doing the net ionic equation. Okay, so I would be pointing to my solid, PB3, parentheses PO4, parentheses 2 as a solid. And I would then write on the other side what things made that up. Oh, well, I needed 3 PB, 2 plus aqueous to come together with 2 PO4, 3 minus aqueous. Now, if you can do that, you can also put back in our spectator ions to make it a full ionic equation. But we just have to put them on both sides. I would look here and I'd say, oh, there's 6 sodiums ions on both sides, and there's 6 nitrate ions on both sides. So that would be my full ionic equation. So you can do that too. Okay? All right, let's do one more. Oh, let's put this one back in G. We've got to find out where sodium phosphate and lead nitrate cross on that grid. We need to put them in there. Did you find it? It'll be in the second column. I'm not sure exactly where in the second column, because that's where your lead nitrate is. So find sodium phosphate and where lead nitrate cross, and that you're going to put lead phosphate in. Did you find it? That's probably the hardest thing. As you go in order, it goes down the first column, then it goes down the second column, then it goes down the third column. So you can just go back and forth easily, but I'm jumping around. Okay, so we're going to do one more together. Sodium phosphate, so I got Na again, PO4 again, 3 minus, but this time I've got calcium, Ca2 plus, and chlorine, Cl minus. So this is L, I think, or I think it's L. Okay, so this was a plus in the center, so that tells me I need to stop there. So sodium and phosphate, we've done this one before. We needed 3 sodiums with 1 phosphate, and everything on this side was AQ. If I didn't remember that, that's group 1 metal, and so it'll be soluble. Plus calcium and chlorine. So calcium is Ca. Chlorine, we need 2 of those, so Cl2. This one fits under group 17 metals, and group 17 metals are only not soluble when they're with lead, silver, and mercury. So this one's okay. It's not the castor bear. Castor bear is only with sulfates. Okay, so this one is AQ. Yields. Okay, now I'm going to do the outsides. So the outsides here, sodium with chlorine. So NaCl. This is both group 17 and group 1 metals, so these are both soluble, AQ. They don't have to both be soluble in order to be soluble. Only one has to be soluble. Okay, plus we do the insides, calcium with phosphate. And here we've got to do another trick again. What goes into both? 6. So how many calciums do I need? 3. How many phosphates do I need? 2. Okay, and then we go through NAGSAG. No nitrates, no acetates, no Group 1 metals, no sulfates, no ammonia, no group 17 metals. So this is our solid. Okay? Be careful because there is some that don't have any solids. And if that's true, then on number 2 you'd put none. On number 3 you'd put none. Or number 3 you'd list all of the ions because they'll all be spectators. And number 4 you'd put none. Okay? So on this one we need to balance it. And I'm looking again and I'm seeing phosphate, I need to have 2 on both sides. So in order to do that, I'm going to have to put a 2 here. And that makes 6 sodiums. So I put a 6 here. That makes 6 chlorines. So I put a 3 here. And there's my 3 calciums. Okay, so if a group hangs together the same on both sides, you can use them like an element. Okay? All right, so we bring our solid down, calcium carbonate, or calcium phosphate. What are our spectator ions? What doesn't make up the solid? Sodium and chlorine. Good. I don't have to put that there's 6 of each, but I should be able to know that. So if I'm writing the net ionic equation, I can put 6 ions of each on both sides. Okay? Again, what's my net ionic? It points to my solid. Now, it can also point to a gas or a liquid or any other thing that's not aqueous. The only things that are going to break up into ions are aqueous. So if they gave me a gas coming off, it would point to my gas. Okay, so I need 3 calcium ions, 2 plus AQ on this side, plus 2 phosphate ions, 3 minus AQ on this side. Now, again, if I wanted the total ionic equation, all I have to do is add 6 sodium ions to both sides and 6 chlorine ions to both sides, and I would have my total ionic. Okay? So I do a sort of little shortcut backwards than what they usually do. They usually have you split it. I just think it's easier, but you can do it either way. All right. Yep. So we forgot to put this in. So find where sodium phosphate and calcium chloride cross. That would be the 3rd column. And you'll have to find sodium phosphate on the left and go across to the 3rd column and put in calcium phosphate. Okay, we okay to go forward? Okay, so the next thing we need to be able to do is formula mass. Formula mass is very easy. You'll need your periodic table out. If you don't have it out, get it out. You're going to be using it a lot today. If you don't have a calculator, go grab one of mine because you're going to need it today. If you have a calculator, get it out. Formula mass, basic. All you're doing is adding up from the periodic table how many of each element you have in a formula. So for NaCl, we would just go Na 22.990, chlorine 35.45, and I would add those together. Okay? I got those right off the periodic table. So whatever sodium is, whatever chlorine is, and I just add them together. And I should get 58, and that's how many grams are in 1 mole of NaCl. So that's grams per mole of NaCl. That's how we label it. On this next one, calcium, we would look on the periodic table for calcium. It's in the 2nd column, and it's 40.078. If there's 1 in parentheses after, like this one has 1 in parentheses, which is a 4, just use it. Ignore the parenthesis. Okay, so I would just put the 4 there. That parenthesis just means that not all scientists agree on that number, but most of them do. But not all. Okay, then we go carbon, 12.011, and then we go oxygen. There's 3 of them at 15.999, and we just add it up. So go ahead and add it up. We'll report these to 5 significant figures because most things that we do don't need more than 5. Oh, sorry. So somebody add it up. Let's see what we can get for this. Yes. 100.08. Do I have a second? 0.086? Okay, so this one would round up to a 9 then, because we only do 5 significant figures. Okay, and then we just put grams per mole of calcium carbonate. Done. Okay, I'm going to do one over here. I'm going to do number 5, and then I'm going to have you do the other 3. So on number 5 here, we would just take calcium, which we just had over here, which is 40.0784, times by 3, and phosphorus, that 2 distributes. So we're going to go 2 times phosphorus, and phosphorus is 30.974. The hardest part of this one is getting familiar with where elements are on your periodic table so you can find them. Okay, and then oxygen, you have 8 of them, because 2 times 4 is 8, at 15.999. And we add that up. Okay, as soon as somebody gets that one added up, let me know. If you get done with that, go ahead and go on to 3, 4, and 6. See if you can do it on your own. I'll have somebody put the finals up on those. I'll voluntold you. Who gets to put them up? Do you have an answer? 310.17 grams per mole of calcium phosphate. I ran out of room, sorry. There you go. Okay, would you do the others? I'm going to have volunteers. I'll give you a few minutes to do a few of them. Justin, come see me for a sec. I always write down just like you're seeing it, even though I can just do it in my calculator really fast, because I found that if I try and do it in my calculator really fast, I usually end up missing something. And if I've written it down, then I can check it twice really quickly, and I don't have to look up those things again, and I can make sure I've got the same answer twice. Because it's better to check it twice real quick here and make sure the adding's right, or check it with a neighbor, than it is to find out, oh, I did this whole big thing that we're going to be going into, and I had this added up wrong. So, did we get this one added up right? 163.94. Everybody get this? 163.94. Awesome. And calcium hydroxide, did we get 74.092? Okay, good. And for this one, did we get 35.046? All right, we're awesome. Okay, let's go ahead and move forward. We're going to watch this little thing to start it.
Mole is an animal that burrows in the ground.
Or a spot on your chin that you gotta shape around.
But there's another kind of mole that's of interest to me.
That's the kind of mole they use in chemistry.
A mole is a unit.
Or have your heart
Containing 6 times 10 to the 23rd.
That's a 6 with 23 zeros at the end.
Much too big a number to comprehend.
Say you had a mole hang strip around the world, give to each of the 5 alien grown-ups, boys and girls. There wouldn't be a single person down and out of luck, cause everybody in the world will get $1 trillion.
Or say you had a mole of paper stacked up towards the sky. Paper's awful thin, but that pile would get so high it'd reach up into outer space. In fact, I think you'd find it'd go up to the moon and back 80 billion times. A mole is a unit.
Or have your heart
Containing 6 times 10 to the 23rd.
That's a 6 with 23 zeros at the end.
Much too big a number to comprehend.
Suppose a mole of marshmallows fell upon the planet over each square inch of land, and so you think that you could stand it? That layer would be 12 miles high, and of course block out our sun. We're talking close to 5 billion trillion tons.
Well, maybe we could save ourselves if we all started eating 1 marshmallow each second, not 2, cause that'd be cheating. With 5 billion people munching, how long do you think it'd take? 40 million years, and that's without a bathroom break. A mole is a unit.
Or have your heart
Containing 6 times 10 to the 23rd.
That's a 6 with 23 zeros at the end.
Much too big a number to comprehend. Say you had a mole of atoms, the pile would be immense. Should I say the answer now or leave you in suspense?
Well, atoms also very small, you understand. You could hold a mole of atoms in the palm of your hand.
So shake a little sugar in the middle of your palm.
Now you don't want to spill it, so try and stay so calm.
You hardly can imagine
And barely realize
there's more atoms in the sugar
than stars up in the sky.
A mole is a unit.
Or have your heart
Containing 6 times 10 to the 23rd.
That's a 6 with 23 zeros at the end.
Much too big a number to comprehend.
So now we're going to listen to a TED Talk on moles and get you a little bit more what we're going to be doing.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay, so in your notes, there is a mole map that I've printed in your notes for you. It is also at the front of the room. I'm closing this door because we're getting a really cold breeze, and my legs are freezing. It's also up here on the wall, up above you. There's also a mole map on each of the other walls. They're a little bit different. They have a little bit more stuff to them, but that's the mole map. You can look at whatever wall you're at, okay? We're going to be using this as we go through. So I put this on the top so that we could sort of see what's going on here. We're going to be using dimensional analysis or factor labeling, whatever you want to call it, to be able to change from atoms of iron here on the left all the way over to grams of iron on the right. So this is whatever they give you is what you want to start with. So we're going to start with 3.45 times 10 to the 22nd atoms of Fe. The difference between an atom and a molecule is an atom is just an element and a molecule is a compound. Okay? We're going to then take it from here following the red, and we're going to divide by Avogadro's number, 6.022 times 10 to the 23rd atoms of Fe in 1 mole of Fe. At this point, we can cross out atoms of Fe, and we're now at the mole, the yellow in the center. Then we do our next conversion following the red line still, and on the bottom we're going to put 1 mole of Fe, and since this is just an element, all we have to do is look at the periodic table for Fe and find the mass of Fe, which is 55.845 with a 2 grams of Fe. At this point, mole of Fe cancels out. Now, remember when we were doing factor label or dimensional analysis at the beginning, you would times through the top, then when you hit to go divide, you divide, but you put this bottom in parentheses. Now, how many have a TI 83, 84, or 85? Okay, and I'm not sure about the others of you, but if you have one of those right now, put 6.022 times 10 to the 23rd in your calculator, and then hit enter. 6.022 times 10 to the 23rd power into your calculator, and hit enter. Okay, now once you've got that in, you want to hit the stow button. It's right above the on. So hit stow, and then hit your green alpha button, and then hit A, which is right underneath the alpha button, and then hit enter. Now every time you hit alpha A, try hitting alpha A, you should get Avogadro's number. So if you've got it and they're able to stare, 6.02 times. So instead of having to put that in every single time you need it, you just put alpha A wherever you want it. So on yours, now that you've got it saved as a group, alpha A, you can go divided parentheses alpha A, close parentheses, done. Okay? So would you put this into your calculator? Let's see if we all end up with the same number. So times through the top, divide by, if you were able to save it by alpha A. If not, then you just have to put it in every time. If you've got my little calculators, you have to put it in every time. Sorry about that. So multiply across the top, then hit divide, parentheses, alpha A, or put in Avogadro's number, close parentheses. And we started with 3 significant figures, so we should end with 3. Anybody got an answer brave enough to share? Okay. Times 10 to anything? Or not? Okay. Grams of Fe. How many got this? Okay, so we got some seconds on that. Good. So that would be our answer, and we'd be done. Okay. Now, using this as an example, we're going to go backwards on this next one. We're starting now at grams, and we're going to follow the green arrows coming back this way to get to atoms. So starting with what we're given always, 45.23 grams of Ag. The first step would be to look on the periodic table, find Ag and its mass, which is 107.87 grams of Ag. And on the top, I would put 1 mole of Ag. So I'm always trying to get rid of whatever's on top here. I want to make sure it goes on the bottom here so I can get rid of it. Okay? The next step, going across, so I've now gone from grams to the yellow mole following the green arrow. I'm now going to go from the yellow mole to the atoms following the green arrow. So here I put 1 mole of silver on the bottom and Avogadro's number on the top, and it would be atoms of Ag. Moles would go out. So this time when I hit my divide after I times to the top, I just have to hit the divide. I don't have to put parentheses because it's just one number and it doesn't have an exponent or anything. So I can just go times to the top, divide, put my bottom number in, hit equal. So let's see what we get for this one. We should have 4 significant figures because we've got 1, 2, 3, 4 in what we were given. Okay, so go ahead and punch it through. I want everybody to have a chance to try and see if they can do it. When somebody gets an answer, let me know. Let's have somebody else do it besides Valerie this time. It is a lot of staples. So if you want to put the garland on it, crisscross, or if you don't want to, or if you want to do something else, let me know. And then I've got the ho, ho, ho for the bottom. It's just getting laminated. Okay, anybody got one? Answer, be brave. Okay. 2.52. One more. 4. Okay. Times. 10 to the 23rd, and that would be atoms. Sorry, it's not writing very good down here in the corner. Atoms of Ag. Okay, how did I know there was times something? I had times 10 to the 23rd on the top, and there was no times 10 to anything on the bottom, so I knew I had to have times 10 to something on the top. Okay? How many got this answer? Okay, good. All right, so when you're putting it through, you need to make sure that you're looking off to the side on your numbers on your calculator. At the side on the top is a number that is times 10 to that power. So you need to make sure you're watching for that. Because a lot of times kids will give me the answer 2.524 and forget the times 10 to the whatever because they forgot to look across. Okay? All right, let's do some more. What is the mass? So I'm looking for mass. I always look at my thing and say, okay, I'm trying to get here. Where am I? If I have this many molecules, molecules, and I've got a formula. So before I even get started, I'm going to stop over here at the side and add up the formula mass of carbon tetrachloride. So carbon is 12.011. Chlorine, I have 4 of them at 35.45. I'm going to add that together and get that mass up, so I don't have to worry about that later. Because anytime I'm dealing with mass, I'm going to have to add up that mass formula. If I was just going between atoms and moles, I wouldn't have to worry about it. But since I'm going all the way to mass, I've got to have the mass of it. Okay, so 12.011 plus 4 times 35.45. What do we get? $12.011 times or plus 4 times 35.45. 133? 53. 153.81. Okay, that's how many grams per mole of carbon tetrachloride. Okay, so now I can go ahead and start with what they gave me, which is this. So 4.53 times 10 to the 24th molecules of CCl4. And I end up doing it like this because otherwise it takes forever. I write it on top of each other. This is where my pet peeve comes in. They shortened mole by taking the E off, but they didn't shorten molecule. That makes me crazy. So it's all right. So we're going from here to the center. So we're going to use the red arrows again. So on the top of the red arrow it says 1 mole of CCl4. On the bottom we've got 6.022 times 10 to the 23rd molecules of CCl4. Okay, at this point I can cross out molecules of CCl4. Now I'm at the mole, which is the yellow. I'm going towards grams. I'm going to use that bottom conversion. So I've got 1 mole CCl4, and on the top I put what I added up, 153.81 grams. And you'll notice it's grams divided by mole. That's why it fits there, of CCl4. Okay, hit my equal sign, cross out my moles. Again, when I put it into my calculator, divide parentheses, and then close the parentheses when you're done. Go ahead and put it in. Let's see what we got. Yes? The very first, whatever they gave you. So they gave me 3, so I'm going to give them 3. Good question. Okay, somebody new hasn't given me an answer yet. What did we get for our answer? I can do this part, grams CCl4. Got to give me a number though. 3 significant figures. Okay, somebody that hasn't told me. Yes.
Wait, how many?
3.
Okay, 1.16.
1.16. How many agree with that? And I have, okay, what else did you get? Okay? 1,160. That sort of looks familiar. So is your calculator in scientific notation? Does it have a 3 off to the side on the right? 1.16? Okay, let's see. It should be 400, yeah, 400 divided by 6. 500, 600, 600 divided by 6, so it should be around 100. Well, I'm looking at so this, the 23 would cancel with 23 of this, leaving 10, so that would be 45.3 times 53.81 divided by 6. Let me do it real quick. 23 would cancel with 24, leaving 10 on the top. So that 10 times the 4.3 would be 45.3. 45.3 times 153.81, and then divide it by 6.022. I got this. Yeah. Okay, so watch it, because if you've got your calculator in scientific notation, it will give you 1.16 times 10 to the third. That's still okay, because 1,000 is the point where we should be putting it into scientific notation anyway. Okay, so just be careful with that. Okay, next one. How many moles, so I'm just going to the center this time. I don't have to go all the way. I'm just going to the yellow. Are in this many grams of this. So because it said I've got grams and I've got a formula, I'm going to take that formula and I'm going to figure out how many, what's the mass of that formula. So Fe is 55.8452, and nitrogen is 2 times 14.007, and oxygen 2 times 3 is 6 times 15.999. Now, after you do a few of these, you'll probably get oxygen memorized real fast, probably carbon memorized. You'll get a few of them memorized, so you don't have to look at the periodic table every single time. But let's go ahead and add that up. What? Okay. Somebody got an add up for that? About 178, 180, something like that. What do we get? 2 more. 8.5. Okay, so that's how many grams are in a mole of that. I'm not going to rewrite it. So now we're going to start here with the 36.47 grams of FeNO3, parentheses 2. We're only going to do one conversion because we're just going from grams using the green arrow to moles. That's it. We're stopping. That's all they wanted. They wanted how many moles, and the moles are yellow in the center. So here we're going to put 1 mole of FeNO3, 2 on the top, and we're going to put 179.85 grams of FeNO3, 2 on the bottom. Grams will go out. We just take this divided by this. We'll end up with 0 point something moles of FeNO3, 2. So what do we get for our, we need 4 significant figures, so 4 after the decimal. Those aren't zeros. 0.228. Okay, do I have a second on that? Awesome. Okay, so of course we would square or circle our answer. I can use any part of this. I can go from atoms to moles or moles to atoms. I can go from grams to moles or moles to grams, or I can use the whole thing. As long as you can do it, you're doing great. Would I have this map on my 3x5 card? Yes. Okay. All right, next part here. Whoops, sorry, went too far. So I want you to try and do these two on your own. Okay, I'll start them in about 3-4 minutes if you get lost. But I would do these two on my own. Or I want you to do these two on your own. You're going to have to find the mass of both of those. So find the mass first on both of them. Yeah, do it however you'd like to do it. Just make it work. It's all good.
We couldn't make like a makeshift star.
Yeah, we can. There's some colored paper right here. You're more than welcome to use. I'll just put it here. Yeah. Well, it might be. It might be. I think I changed the grams, though. Did I change the grams? Oh, whoa, whoa, whoa. Come on. So as I'm getting these done up here, as you finish, go ahead and check and see if you're doing it right. Okay, how do we do? Did we have any problems adding up the masses? We okay with that? Do we have any problems setting up the conversions? Okay, just watch your mole map. I've set the conversion up for you. So once you add up the grams, all you have to do is plug it in where it says grams. Okay? All right, we okay to move forward? Okay. Maybe. There we go. So now it gets to the point where we're going to put the balancing of the equations together with what we just learned. Okay? So to calculate the mass of aluminum that must be used to produce 500 grams of aluminum oxide, the equation below use the equation below. Don't forget to balance it. So the first thing we're going to do is we're going to balance the equation. So what do we need to do on this one to balance the equation? Take a minute, look at the oxygens. That's going to throw it off. Okay. Four. There we go. Because we had a 3 oxygen on one side, 2 oxygen on the other, so we have to make it to 6, and that throws the aluminum off. Okay, so this is what I do when they're giving me something like this. I put right underneath what I'm trying to get, or what I have. So I've got 500.0 grams that I need to produce of this. They're asking me how many grams of this do I need to produce. Okay, so first of all, I need to get in my head, what have I got to do, where am I going? And since we're using grams here on this formula, I'm going to need to add that formula up. So 2 times aluminum, aluminum's 26.982, and oxygen, 3 times it, 15.999, and I add those up real quickly. Nope, you don't do the 2 in front, just the formula mass itself. Okay, we'll do the ratio in a minute. It's sort of like a recipe. Okay, so 2 times 26.982 plus 3 times 15.999, and I got a syntax error. What did I do? I hit the funny thing instead. Okay, 101.96. Is that what you guys got? Okay, so I have to work backwards. I start again with what they gave me. They only gave me one number, which was the 500 grams of aluminum oxide. Before I can use the recipe, I have to get it into moles, because those numbers, those red numbers, represent a mole ratio. So I've got to get it to moles first. So the first thing I do is use my mole map, and I say, okay, in 1 mole of aluminum oxide, there are 101.96 grams of aluminum oxide. So I can figure out how many moles I've got. Once I get it to moles, then I can use a mole ratio. My mole ratio is the coefficients. So I want to get rid of the aluminum oxide, so I put the mole ratio for aluminum oxide on the bottom. For every 2 moles of aluminum oxide, I need 4 moles of aluminum. Moles of aluminum oxide go out. Now they ask me how many grams. So I'm still not to grams, but I got to moles of aluminum. So my next conversion goes from moles of aluminum back to grams of aluminum. So in 1 mole of aluminum, now I just get the aluminum's mass off the periodic table. So that's 26.982 grams of aluminum. At this point, I can cross out moles of aluminum. Okay? I'm going to hit times to the top, hit the divide, parentheses, times to the bottom, close the parentheses, get my answer. Would you plug that in? Let's see what we get. Make sure we all get the same answer. So we're just adding one more step where we use a balanced equation to go from moles of something to moles of something else. Oh, they're blinking ones.
Okay, nope.
Yeah, that's why they're here, is because they're ornery. Yeah. Okay, anybody got an answer? So there's a decimal right here. Because there's a decimal, we get 3. Okay, so give me 3. Yes?
I
Okay, would it round up to 265? Yeah. Okay, awesome. 265 grams of aluminum. Okay, so you should be able to do things like this. Okay, let's see if we got another problem we can do a question with. Okay, so when we're doing things like this, a lot of times they'll give you two reactants, and they'll say, what are you going to run out of? What do you have excess of? So it's sort of like making peanut butter and, not really peanut butter, like bologna and cheese sandwiches. You have this much bologna, you have this much cheese, you have this much bread. How many sandwiches can you make with two pieces of bread, one thing of cheese, and one thing of bologna? One of them you're going to run out of first. And more than one of them you're going to have excess of. Okay? So that's just the definition of what they're talking about. Limiting means I'm running out of it. And excess means I have extra of it. So here's a hot dog analogy here.
Can you go back just for a minute? Okay.
You okay to go forward? Okay. So here's a hot dog analogy. See, if I have 5 hot dogs and I only have 4 hot dog buns, then I can make 4 hot dogs and I have one that doesn't have a bun, right? So the limiting reagent here would be my buns. My excess reagent would be my hot dogs. If I had hamburgers, it's more complex. As we get more complex in the reactants, we have more than 2 reactants, then more things can be excess. You'll notice here we have 3 hamburger patties, we have 4 buns, we have 6 cheese, and we have 7 tomatoes. If I'm to make 3 hamburgers, that's the limiting thing here is my hamburgers, okay, my patties. But I'm going to have excess of cheese, tomatoes, and buns. So I'm going to have more than one thing in excess. And that can happen. So here we go. A sample of 4 grams of methane. I always write what I've been given. Let me use a different color. 4.00 grams of methane is mixed with 15 grams of chlorine. Determine which is the limiting reagent. Well, the first thing I need to do is make sure my equation is balanced. Okay? So, is it balanced? No, it's not. So what do I need to do to balance it? Well, my chlorines are off. If I fix my chlorines, well, let's not do the chlorines first. Let's do the hydrogens. So 4 hydrogens, I need 4 hydrogens. I'm going to put 4 here. Now I have 4 plus 4 is 8. So if I put a 4 here, does it balance it? We balanced now? Okay, so for every 1 mole of methane, I need 4 moles of chlorine. Okay? So I'm trying to figure out which one I can make. So I got to add this up. I got to add my mass up. And I got to change these to moles. So I'm going to take 12.011, which is a carbon. I'm going to take hydrogen, 4 times 1.008. And I'm going to add that up. I'm going to take 2 times chlorine, 35.45, and I'm going to add that up. Okay? Well, this one's going to be what? 16.3013, something like that, grams. And this one over here, we're going to end up with 70.90. Right? I'm just doing it in my head, so if I did it wrong, let me know. 4? Is it 4? Thank you. Okay, so all I have to do now is find out which one I have less of. So now I'm just going to take that 4 up there, and I'm going to go 4.00, and I'm going to divide it by this to get an answer. I'm going to take that 15.0 and I'm going to divide it by this to get an answer. That will give me moles. That's what we were doing. Okay, so if I'm looking at my mole map, I'm trying to get to moles. So I'm going to divide by the grams. So 4 divided by 16.014 gives me 0.24, actually 0.250 moles. Okay, if I take 15 divided by 70.90, I end up with 0.212. Come on. Play today. It's saying it's had enough. We might stop after this one. Okay, well, we're just going to rewrite that one really quickly. 0.212 moles. But my ratio is 1 to 4. So for every 1 methane, I need 4 moles of chlorine. For every 0.25, I don't have 4 times that in chlorine, right? I don't. There's no way. So my limiting, what I'm going to run out of, is my chlorine. So my limiting is my Cl2. My excess is my CH4. And I can say that just by looking at that, because I need 4 times as much chlorine, and I don't have it. Because 4 times 0.25 is not 0.21, right? Okay, so now what it wants to say is, okay, then how much carbon tetrachloride can be formed? I take my limiting, which I kept the mole, so I don't have to do more work, and I'm going to start with 0.212 moles of chlorine. And I'm going to use the ratios here. I'm going to use this ratio to this ratio. So for every 4 moles of chlorine, I get 1 mole of CCl4. Okay, mole of CCl2 goes out. Then I've got to go, oh man, I got to add up carbon tetrachloride again. So carbon, 12.011. Chlorine, did we do this already? 35.45. I thought we added carbon tetrachloride up already. So we add that up, 12.011 plus 4 times 35.453, 153.82. So I'm going to put that on the top, 183, nope, try that again, 153.82 grams. And on the bottom, 1 mole, CCl4, CCl4. Whoops, that's not going to be a divide line. It's just going to be equals. Moles go out. They asked me what's the mass. Mass is grams. So I'm going to take that, times it by 0.212, and divide it by 4. And we have 3 significant figures, so 8.15 grams of CCl4 could be produced in a perfect world. Okay, now, here's where it gets a little tricky. Not too bad, because we can go back, and as long as we've written these down, it's not too hard. Okay, what element or compound is the excess? We found that already. That's CH4, right? How much is not used? So now we've got to go backwards. So if we take that 0.212 moles again, which was of Cl2, we want to find out how much CH4 was used. So we're this time going to use this and this as the ratio to go backwards. So going backwards, we're going 4 moles of Cl2 on the bottom, 1 mole of CH4 on top, and since it was not, how much was not used, and they gave us grams, we're going to have to go back to grams. So mole went out, and we're going to go one more step, 1 mole CH4 and 16.014 grams CH4. Moles go out. So plugging that through, 0.212 times 16.014, and then divide it by 4. So we used 0.849 grams. That's how much we used. We had 4 grams. So to find out how much was not used, we're going to take that 4 grams and subtract 0.849, and we end up with what we didn't use. So 3.151 grams not used of CH4. Okay? Now, we've covered a lot of new stuff today, and I want to make sure we hit it again next time, so I want to leave the next page for next time so we have some time to redo that again. Hopefully it'll get in your head. I know you have only about 8 minutes, but if you would use that to do...
It's like start.
Oh, 3 minutes, 2 minutes. Okay. Yeah, I forget late start. Okay, so we'll come back and hit it again next time, the stoichiometry, but this gets you through a lot of it. Would you please try on your own to get some of these done in the lab? This is not a lab that we have to do, but I found that if kids actually write this and do this, when you get to the test, it's second nature. You know how to do it, you know what to do, and it makes the test a lot easier. We are going to do this lab next time, but it only takes like 5 minutes back in lab, and then we're going to come back in here. It's just drop, 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 see, ooh, ah, and then come back to see how your predictions are. So if you'll do those, and if you need help, if you're not getting how to write the equations and that, come get some help, okay?